Okay, I will call all our great speakers for this session to come up in front of the stage to join me. First, Mrs. Rohani Amburampe from Hasanuddin University. Please give it a big applause to Ibu Rohani. Finally, we met again. Bu Rohani, how are you? Please sit down. And then Ibu Devi, and I'm sorry if I'm wrong to pronounce, Kosin. Ya, Kusin Bu ya. Ya. Mohon maaf Bu kalau ada kesalahan. Silakan kita berikan aplaus. Dari ITB, next is Mr. Wawan Kiswara from Indonesian Seagrass Foundation. Let us a big applause to Pak Wawan. Applause is also for exercise. So we have a great motivation today because this is last session. So don't hesitate to make applause. Ya, silakan Pak. And next, Mr. Aan J. Wahyudi from LIPI and MMAF. Thank you for the big applause. And Ibu Yusmiana P. Rahayu. Okay, thank you. Pak Andri ya. Okay, Pak Andri Rewan, thank you. So Pak Aan cannot attend today, so Pak Andri Irawan will become the speaker for Pak Aan Wahyudi Research. Ibu Yus, and finally the last.
My name is not Yusmiana, but
okay, Ibu Mariska. Also Ibu Yusmiana cannot attend, so Ibu Mariska will become the speaker for MMF GMT Germany and Coordinating Ministry of Maritime Affairs. And last speaker, Ibu Atika Rahma from University of Indonesia. Let's give her a big applause. If you feel a little bit hungry because your applause is not so big now, please come out and take a coffee, but don't bring inside, please. Okay. Okay. Thank you for coming today for all the speakers. We don't have much time. I know it is very tempting to say a lot about your research because researcher and lecturer always don't have time enough to say everything interesting about their research. Please, because we have only 90 minutes minus I think 15 minutes because the last session already taken our session. So I hope you can give your presentation maximum 10 minutes. If I already move my body like not so comfortable in my chair or sofa, you can know that time is almost out. So I'm sorry. First speaker will be Ibu Rohani Amburampe. Time is.
okay. Thank you very much. Good evening, everybody. Just be quick that I'm going to present about the variability in the carbon storage of seagrass habitat. Next, please. So seagrass, I hope everyone's here have looked this aquatic plant. So this is one of the important blue carbon beside mangrove and macroalgae. Mangrove is very popular, but this one is getting to be popular. So what the seagrass? Seagrass is the only true flowering plant that can live completely underwater. That's why we cannot see seagrass easily because they are inundated underwater. So, and then they process through roots, stem, and leaves, and then require physical conditions to occur or to live. Very important for ecosystem, marine ecosystem. So ecosystem services of the seagrass is huge. And then that we're going to talk about the seagrass capacity to sequester carbon as an important carbon stock. Next, please. And then there are three major carbon storage in seagrass that usually we measure. We can measure above ground living biomass, so living tissue, And then below ground living biomass, that's roots and stem. And then the important things is soil carbons. Next, please. We know that seagrass distribute all over the world, except Antarctic. And then we know that they live in different level of environment. And seagrass globally is estimated about 177,000 kilometers square. That's a huge potential. And then even this number is still underestimated because it's not including Indonesia yet. So this number is still small compared to the real number of the seagrass area that we have globally. And then we know that seagrass also declining about 7% per year. Now we don't know. In Java, they're already declining more than 40%, Pak Wawan, according to Pak Wawan research long time ago. So area of the seagrass is declining. That's give a consequence to the declining of the ecosystem services also, and then the capacity of the blue carbon. Next, please. The variability of the seagrass as a carbon stocks was affected by many factors, including seagrass species composition. So we have about 72 species of seagrass worldwide, and then in Indonesia we have about 13 species of seagrass. And then also the type of the bed. We know we have a monospecies seagrass bed that comprises only one species of seagrass, and then the other one is multi-species seagrass bed that comprises more than one species. In Indonesia, very common, we found one seagrass bed comprises more than 3, even 8 species occur in the same bed. So this is, of course, influence the carbon storage of the seagrass, because we know that different species have different morphological characteristics, and then morphological characteristics will influence the biomass, the density of the seagrass, and also influence the carbon storage capacity. Next, please. And then this is the about 72 species of seagrass with range of morphological features, from the really tiny one to the giant one. So in Indonesia, we have the climax species, we call it Enhalus acroides, and also we have the small tiny one. But we couldn't underestimate the small tiny one, because according to my research, even the tiny seagrass one, they also have significant blue carbons in their living tissue. So there is a variation in morphology and then biomass, because above and below ground. And then we know that seagrass, if they are big, they're able to penetrate the root deeper than the smaller one. So also influence the carbon stock in the soil. And then there is also variation in growth dynamic between species. The tiny seagrass maybe just live about 3 months, but the bigger one could be many years. Next, please. So this is, I took it from Lavery et al., 2013. So he compared the carbon storage between the species. So in Australia, it's easily to compare between the species because they have a lot of monospecies bed. But in Indonesia, it's quite hard because most of the seagrass bed that we have in Indonesia is multi-specific. So we can see that actually seagrass species have their own characteristic to store carbon. Next, please. And then also the habitat. We know that seagrass can occur from the estuary to the sea. So also this parameter or environmental parameters also affect the capacity of the seagrass to store carbon. Because, yeah, they occur in different environmental factors. And then In terms of seagrass habitat also, seagrass distribute all over the world, and then they occur in different latitude. We know that they have a different adaptation to the environmental factors, temperatures, and also could influence the carbon store capacity. So this is my recent study on seagrass carbon. I would like to see if seagrass live in different wave exposure, do they have a different capacity to store carbon in the soil? So I choose a range of the locations from the very exposed one to the less exposure site in Spermonde archipelago in Makassar. Next, please. And then this is the seagrass characteristics that I choose. So mostly multi-species, but in the closed site, they are dominated by Enhalus. In the middle hydrodynamic site, there are more species live there. And then in the high exposure site, also less species. Next, please. We just going directly to the result. I'm not going to talk about the methods, how I collect the data. But we can see the characteristic of the seagrass in different locations. So we can see leaf density, biomass in different hydrodynamic conditions. We can see that statistically it's not significant, even though we can show the patterns. Next, please. Now we're going to the carbons. That's the most important things. So in terms of carbon organic in living materials, this is above ground, the green color, and below ground, the red color. And so carbon stored in the above ground biomass was significantly higher in higher exposure locations on the right side compared to the medium and low. But the opposite happening for the below ground. So for the below ground seagrass, they're more or significantly higher carbon they store in a low exposure site compared to the other one. Next, please. And then this is the profile, because I took also the soil or the sediment sample, and then I slice it every 5 centimeters, and then try to make a profile how they look like from the surface to the deep. And then we can see that seagrass that we have in Spermonde archipelago only contribute about 15 centimeters to the soil. We can see that they are higher up to 15 centimeters, and then they decrease. So the carbon organics in sediments decrease along the depth. So this is a pattern of a decrease in carbon organic in seagrass sediment with increasing sediment depth. It means that the contributions of the seagrass in carbonate environments like in Spermonde archipelago just up to maximum 25 centimeters, because the root penetrations of the seagrass that we have is not really deep. Next, please. And then I try to analyze the data using a statistical software, and then actually the sedimentary carbon content, because I just able to analyze the 15 centimeters due to the data, and then they are significantly lower in the high exposure site compared to medium and low. So the high exposure site, it looks like the sediments so they experience like, because of the wave exposure is so high, so the porosity of the sediment is increased, and then the grain size is become bigger. So they cannot really capture the organic content, including the carbon.
Ibu Rohani, I'm sorry,
yeah.
your time almost up.
Nearly done. Next. Okay, I'm not going to talk about this. This is just comparison with other study that they have a similar pattern with this study. And then next, please. It's okay. So the conclusion of this study that different level of hydrodynamic have effect on seagrass community present in the area, and our result confirmed the importance of environmental variability in carbon capture, so need to take into account. Thank you.
Thank you. Give a big applause for Ibu Rohani. Apparently, I make a big mistake, and my head and my neck is almost have a pain. So, shall we go to the front row for all speakers? I'm sorry for this trouble, because we would like to see the interesting presentation. This is after discussion. Then, when discussion, we will go up to the stage again. And Ibu Devi, please.
Thank you very much, and good afternoon to everyone. I think we have heard a great deal about blue carbon and blue carbon ecosystems since this morning, so I will not repeat some of the theoretical background and general information. I think the previous speaker also talked a great deal about the theoretical background. So I think we can agree that, or I think most of us here will agree that blue carbon is important and Indonesia has a great potential. And for various reasons, for various important reasons, there is a need for us to be able to quite accurately estimate the amount of carbon or blue carbon contained within the seagrass ecosystems. So, next slide, please. So this is the background theory. I think we all know this. We may probably see in similar slides today. But what I would like to focus on is as the title refers to, is how should we more accurately estimate the blue carbon within seagrass ecosystems. So if you would look, next slide. If you see here, you can see that this is from the left figure. You can see that if you compare different ecosystems, seagrass, this is a figure from Fort Korean 2012. There is quite an amount of variation. So if you look at wetlands, coastal wetlands in general, mangroves and salt marshes tend to be higher in terms of per area storage. But seagrass meadows, because they most probably cover a larger area, then it is estimated that they will have a higher global sequestration rate. But the problem is, and this has been emphasized in a number of studies, is that there is much uncertainty about the data because there is a lot of variation. There's a lot of variation in the methodology used to collect the data. So, this is what I found, for example, in our study. We are currently doing some blue carbon studies, specifically inventory studies in Java. These are research sites for this year. We are looking at both mangroves and seagrass meadows. Why are we focusing on Java? Well, of course, we know that Java is the most densely populated island. The ecosystems are being threatened, yet at the same time, we are more dependent on the ecosystem services they provide. So while other people, maybe the studies that have been presented today are outside of Java, we are looking at these sites, and maybe I just give you a little sampling of some of the data that we have. So seagrass, we look at the areas here. I'm going to show you the data from West Java and in Sanchang, it's in the southern part of West Java, and East Java in Baluran. Just a sampling of data to show you just the kind of figures that we are getting. And as hypothesized based on the theoretical estimates, the largest portion of carbon was found in the substrate or below ground, while the live biomass is relatively very small compared to the soil content. And we found this in all sites, all locations that we have measured so far. So this is our data, the range that is in our study sites, and if you compare it to the other locations, it may still be within the range that has been reported, but you can see that the range is very wide. There's a really great variability. So this is something that I think the previous speaker also mentioned. There is great variability, and some of that is due to the difference in methodology that is being used, and so that they may not be all comparable. So I think if we can look at it, that there's maybe three issues that we consider, three main issues that we should consider when we speak about the methodology. The first is the technical issues, that is, how are we collecting our data, in other words, the field data. And then the second is the conceptual issues, the theoretical and scientific basis of the methodology we use. And the third is the analytical issues, and that is, how do we analyze our data and draw conclusions from it. So technical issues, this is just a general view. Of course, those of you who have gone out to the field and actually collect data, you know that it's not easy. For example, if you look at seagrass, you have to take into consideration the temporal dynamics, whether you are going there at low tide or high tide, or whether you have to, you can sample at a time like this. It would be very nice if you could sample the left picture there. But if you have to go down and dive down, it's a pretty different thing. Of course, you have to plan your work, but that's easier said than done, because sometimes we go out to the field and it turns out it's high tide, and it's not as easy to sample and to measure. So the temporal dynamics, so the spatial patchiness related also to the difference in communities, the different species that was mentioned, whether or not they were monospecific or heterogeneous or multi-specific. So these are just some of the factors that we should consider when we think of it. Some studies have been conducted on these aspects of the seagrass, but it should be remembered that there are variation, as mentioned, variation because of the species and its characteristics. Different species are very different in size and in biomass. So when we talk about a monospecific contribution to carbon, it's a very different figure when you look at the large species and the small species. Depends also on the plant density and morphology, nutrient availability, the size of the meadows and the patchiness, and of course the surrounding environment, the wave exposure, the daily and seasonal annual patterns, the substrate type, and the other factors that affect the carbon decomposition and mineralization, because that is what then becomes the carbon storage that is very important in the seagrass ecosystems. Just analytical issues, for example, when you already get your samples from the field, and then how do you measure it? For example, how do you estimate the live biomass? There are destructive methods, there are non-destructive or semi-destructive methods. For example, I think the Blue Carbon Initiative, the protocol states that you just take you don't look at the species, you take it as a whole, whereas, as mentioned before, there are differences between species, so that's something that you should take into consideration. Or you can do it the semi-destructive. In other words, what you do is you look at the density and then you try to make a conversion factor so that you can calculate the carbon stock without having to take too much destructive sample from the field. So that's just some example. Also, when we talk about the substrate, if you've been out to the field, you know that it's not an easy thing to do. And especially in our seagrasses, sometimes the substrate is very hard. It's a sandy or gravelly. That's one thing. And when actually the stored carbon is within the substrate itself. So for example, sometimes in order to standardize, we look at the 1 meter depth. And in reality, sometimes we can only go down to 1 meter because it becomes much more difficult to sample deeper. But that then does not give you the correct illustration of what is actually there.
Ibu Devi, I'm sorry. Okay, summary. Great timing.
Okay. So just maybe it's not a conclusion, but a summary just to emphasize a few points here. That we need proper quantification. Yes, this is what we need in order to contribute to the policy initiatives about blue carbon. However, there is still variation in the methodology used, and there are certain aspects, including the scientific basis, that will still need to require further study. And there are still gaps in knowledge and the need for scientific data on carbon sequestration from a range of geographical locations. Specifically, of course, we're talking about in Indonesia. Thank you.
Thank you very much. Give a big applause for Ibu Devi. The two speakers, very good in managing time, so I hope the last 4 speakers also. Pak Wawan?
This is slide. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. First of all, I would like to thank to Prof. Daniel Mudiarso for his invitation. Actually, when I received the email, I have no plan to attend this meeting because I already retired in 2016. But in the evening, around 10 o'clock, Pak Daniel phoned me and please come just to share your experiences for Seagrass studies. Thank you, Pak Daniel. My topic is Seagrass and carbon studies in Indonesian waters. I work as research center for oceanography at LIPI, and then I joined in Lamina, Yayasan Lamun Indonesia. Actually, we already heard from Bu Rohani about seagrass and concept about the carbon studies from Ibu Devi. Maybe I not repeat anymore, but I am just to complete for their talks. And next. Here the seagrass, no seaweed. We are clean. A clear seagrass has a root, rhizome, leaf, and roots and fruit. But seaweed only has a hard part and thallus. Next slide. Here's some example from Amphalus. It's a seagrass flowering plant in the coastal waters. Here's complete Amphalus. Here's flowers, female flowers, seed, fruit, and pollination, and male flowers. Next. Here from Arber, the seagrass are marine plant, can live in saline medium, can grow when completely submerged, have anchoring system against wave or currents, have capacity for hydrophilous pollination, can compete with other organisms in the stable or unstable marine condition. Next. Here, where are they growing? Tidal. They subtidal, always underwater to the depth for 40 meters. In the tidal, exposed to the air during low tide. Water clarity, clear water, and turbid water. Type of substrate, they can grow on mud or slit, fine sand, coarse sand, coral rubble, mix of substrate, even on massive stones on the dead coral. And neighboring ecosystem, a coral reef and a mangrove, maybe can be used for issue from the Bu Devi, how to collect samples for seagrass. We homogenize the area, how to collect the samples according to this, because in the seagrass they have biotic and abiotic factors. abiotic factors can decide to collect the samples. Next. Seagrass in Indonesia is 15, but only 13 to species only in herbarium, number 7 and number 12, Halophila beccarii and Halophila rufia maritima. We found it from herbarium. Next. Here, repeat from Bu Rohani. We call monospecies vegetation, and then mixed vegetation from 2 to 8 species of seagrasses. We can see from the pictures. Next. Yes, history of seagrass studies in Indonesia before 1970, pioneered by Zollinger, 1848, until Kostermans, 1962, collected seagrasses for herbarium collection who used by Den Hartog, 1970, as the material for writing the book, The Seagrasses of the World, including taxonomy, distribution of seagrass, ecology and seagrass from Indonesian waters. Next. Years. Den Hartog never been to Indonesia, but he can make book from herbarium. Herbarium is not rubbish, but very important data for seagrass. Next. And from after 1970s, at present, special composition and abandoned office in the seagrass bed of Burung Island, Padi Island, Jakarta, by Hutomo and Waktusowo, 1977. And then PhD thesis of Hutomo, 1984, who introduced the term of lamun for seagrass in Indonesia. The seagrass ecology in Indonesian waters was started in 1984 during Seaweed expedition 2. Next. Years. Yeah, when I was young, 30 years ago, yes, actually this is basic for studies of seagrass in Indonesia, 1984. Next. And here there's research for production and consumption of seagrass by using methods, bell jar, light, and dark bell jars. Clean the boom, that's found net production 60 to 1,060 carbon per meter square per day. And Eptemeyer, from his PhD in subserviency, found less than 500 carbon per square meter per day. Next. Here's the seagrass study by Indonesian water scientists. Based on the experience during the expedition 2, study on the structure of ecosystem, type of substrate, water depth, zonation, space composition, distribution, types of vegetation, percent cover, density, and biomass of seagrasses. Study on the growth, production, and decomposition of seagrasses. Next. And then study on association biota of the seagrasses, mollusks, echinoderm, polyhead, crustacean, and fishes. Study on the gut content of seagrass species. Study on nutrient content in the interstitial water and water columns of seagrass beds. Study of heavy metal in the seagrass bed. Study on degradation due to reclamation activities at Banten Bay. Dugong in the aquarium, Surabaya Zoo, and Ancol, Astronaut and Seaweed Indonesia. Uptake and allocation of carbon 13 by aerosols at differing light ability. And then transversion of seagrasses and colonies of data. And the last, carbon stock and sequestration in the seagrass beds. Next. This is how to collect samples. Use random. The pictures, and then these pictures for leaf marking method of seagrass. And here for leaf litter fall using a cage from net. Next. And according to my opinions as ecologist, actually it's a function of seagrass as carbon stock and carbon sequestration is our stuff with new name. Barang lama, nama baru. Because our staff values of biomass and production of seagrass in gram dry weight of area time as seagrass beds, and UNIM the values of biomass and production in gram carbon area time as global change. Study on study on community and productive of seagrasses, biomass and production data in dry weight is converted into carbon. It's the key of blue carbon. Actually, this is not new. This is barang lama, nama baru. Next. Here is a movie about the degradation of seagrasses in Indonesia. This Bu Rohani already mentioned that around 0.9% per year before 1940, and now around 7% per year since 1990. And it's estimated that 29% of seagrass bed global distribution has been lost since 19th century, Wycott et al. 2009. Next is some how the cause of the loss of seagrass. The first is natural love for grazing from sea turtles, and here from wave. You have also from waves and currents. You also from wave and currents. Next, and then anthropogenics. Here's pictures from Banten Bay reclamation, and then here's for seaweed cultures, and then here for effect of from refinery sugar in Banten Bay, blooming of caulerpa, almost 60 centimeter depth of caulerpa, and from household waste. Next, here in Pari Islands, in front of our place in Pari Islands, in Pulau Tengah, they use for villas on the Pulau Tengah. They dress seagrass on the Pulau Tengah, and then makes villas. Next, and then the cause is sun sucking. This use this one, and the research almost 2 meters depth of the seagrass bed to collect sands to make the iron much bigger. Next, and here for the people, because Pari Island as tourist destination, people use this to build their houses, homestay, and so forth. And this is the effect of sand mining. Next, this is from Jakarta. Also, we saw from Padaniel plastics. Actually, this problem in Indonesia when I was still working. When we went to Jakarta Bay, our boat stopped because propellers was cut by plastic bags. And 2012 by Pak Andri in Ambon, we found the same problems. Plastics in the sea. Next. Aim of the presentation, data on carbon stock and sequestration as baseline information for global change research and mitigation. And then to find the cheap and easy method of transplanting seagrasses for restoration of degraded coastal ecosystem to enhance its function as carbon stock and sequestration, physical and ecological function aspects. Next. Next. Here are some results. This biomass of some seagrass species. The highest is from Evalus, 322.6 gram, and the lowest is Halopila ovalis. Next. This carbon stock and sequestration in some species, and Ochorides, Simodosea, and Thalasia. Next, because of times.
Yeah, almost.
Almost. Next, here's a liter 4 using cats in next. Now, maybe this important to increase the carbon stock and its sequestration through the seagrass bed. We can do by management and conservation of existing seagrass bed through marine protected areas, national, province, district, and village level. This picture is village level in Tanjung Pinang to protect seagrass. Next. The transplantation of seagrass very costly, difficult, and challenging. Not right at all 2015. Next. This is the techniques, manual, anchor, and on anchor. And then next. This machinal, EcoSub in Australia, GATS in USA, and here is using equipment in the Netherlands. Next. And here we use linggis, crowbar, to plant seagrass. Very cheap, very easy method. Next. Some samples. Next. We start in 1984 in Pulau Pari. Next. Next. This failure In Banten Bay, due to muddy substrate, wave and barnacle and worms. And then in Bidadari Islands, wave and currents, and in Pairan, turbidity, depth, and temperature. And then next, and successful in Banten Bay, using single shoot of Enhalus and split of Simuricea cellulata, and in Pari Island, single shoot of Enhalus and split of Tertia hembricii. Next. And then plant technique, very easy, use crowbar or wood and bamboo. Next. Here's some lizard. The critical time for transplantation is 6 months. After that, they can grow. After 6 months, they can survive. Next. Here's some example for bare area planting with seagrass. There's biota increase, and maybe we can join with the local people. If we planting seagrass, the animals can come to that area. Next.
I'm sorry,
Yeah.
but
Next. Yeah.
we already 3 minutes up.
Yeah. Here, example. Next. Here, the sperm of the old people until the the primary primary school. Next. It's a function to conserve and protect the extinct grass beds and to restore regrade them are important to maintain carbon stock and in the coastal zone. The cheap and easy method of transplanting seagrasses can be used for restoration degraded coastal ecosystem, and hence it functions carbon stock and sequestration physical and edible function aspects. Next. Also, once again, thank you for Daniel for special invitation to attend this meeting. Yeah. It's from a student from Japan doing transplanting seagrass in Pari Island. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you very much.
Sorry, this time more than 10 minutes.
No problem, sir. So very interesting. The blame is for time, not for you, sir. Very interesting. And next we call Bapak Andri Irawan.
Good evening. Assalamualaikum warahmatullahi wabarakatuh. Okay. I would like to present our team effort on measuring the carbon stock and uptake potential by seagrass meadows and also the mangrove ecosystem in Indonesia. Okay. The background of our work is about the Indonesian National Action Plan for Greenhouse. We are committed to reduce our greenhouse emission by 26%, but however the target is still focused on the land-based sector. So in this presentation we want to promote about the potential of the coastal vegetation for the reducing the emission. Next. Okay, why it's very important? Because beside the land-based plants, we also have the coastal vegetation like mangrove, seagrass, and seaweeds. They also absorb the CO2 and make them into biomass tissue and also exported to sediment. So we can call it blue carbon. They are reducing ocean acidification also. That was very dangerous for the coral reefs. So besides reducing the climate change effects, they also reducing the ocean acidification. So it was one of the goal for climate change mitigation. Next. This is our methods that we use. Okay, maybe we can skip it. Next. Okay, this is one mangrove. Skip also. Oh no, back. Okay. We have estimate because of the one map policy in Indonesia. We have 150,693.16 hectares of seagrass that we are verified. So it was the largest area after Eastern Australia, and this is a great potential for carbon uptake and storage. Next. This is mangroves. Next. Okay. This is our data from LIPI and fisheries KKP, because we are now realized that the sea is very large area that we cannot study by ourselves. So at this initial phase, we embrace our neighbor in Ancol because it's very near. So the coordination is more easy. Okay. Okay. Back. Okay. As the previous presenter said, that there are many variabilities in seagrass in counting the carbon. As you see in different places, and the the value will be different. Okay, next. Okay, as the conclusion. Okay, the seagrass we measure by our primary data that they can uptake until minimum of 24.13 ton of CO2 per hectare per year, and this will be converted into their biomass on 0.94 tons carbon per hectare, and most of them will be go to the sediment around 558.35 ton carbon per hectare. Okay, this value can be used to for the stakeholder to count how many hectares that they need to reduce the emission in their area. But this is only from our data, LIPI and KKP. If we can collaborate with more data from university and other agency, the number will be more accurate. So at this occasion is very good opportunity to make the network of our data. Next. So the conclusion, yes, the seagrass is still have a low percentage on carbon storage than mangrove, but they also are important vegetation for this carbon. Next. Okay, so in our data we have some recommendation that conservation and rehabilitation of mangrove and seagrass ecosystem are useful for maintaining their surface on carbon absorption. The exploitation and less appropriate management on regional development will likely reduce the coastal vegetation area. That in turn will need policy intervention by integrating regional development with coastal ecosystem preservation. That can be a solution. And the last one is low carbon development planning needs to add coastal vegetation conservation and rehabilitation component as contribution of marine sector on climate change mitigation action. Okay, this document will also presented by our team to Bappenas in next month. I hope this document will promote the seagrass and mangrove area as an important area for the greenhouse emission reduction. Okay. Okay. This is our appointment to LIPI, KKP, and also CTI for funding our project. Next. Thank you. And discussion are very welcome. Thank you.
Thank you very much, Andri. And we will move to the next speaker, Ibu Marisa.
Terima kasih Bapak Moderator. Good evening. Assalamualaikum warahmatullahi wabarakatuh. Let me introduce myself first. My name is Mariska Astrid. I'm from KKP, Pusriskel KKP, Ministry of Marine Affairs and Fisheries. I'm going to talk briefly about sources of organic matter in the sediment in Speramonde Archipelago. Next. Before I continue with my topic, I would like to briefly highlight about what the research that we have been doing since 2011 up until now. We have covering plenty areas. This is not only for seagrasses, but also for mangroves. And these data are being prepared as an input for recommendation for the National Action Planning for greenhouse gases. Okay, next. I'm not going to explain in detail about the functions and services of seagrass because the previous speakers have already explained about this. Well, we all know that seagrasses have many functions and services. Next. And recently highlight that seagrass also are an important blue carbon sink because they sequester and they store a lot of organic carbon, particularly in the sediment. And they also have quite high carbon burial rate, which is comparable to other ecosystems. Next. Why? The processes behind why seagrass could store high amount of organic carbon is because they are highly productive and half of their productivity is buried in the seagrass sediment and half of the primary production is exported to the adjacent ecosystems. And because they grow in the transition zone between land and sea, they could trap a lot of organic matter from surrounding areas. And because the sediment is submerged in the water, so the oxygen diffuses very slowly, so the composition rate is low. Therefore, the organic carbon could retain in the sediment for not only for a century, but also up until millennia. Next. So, but we all know that seagrasses are vulnerable to disturbance, as Pak Wayan already also explained. The estimated loss of seagrass globally, which is quite high, and the emission that being released is very high, which is even higher compared to mangroves. Next. And so protecting seagrass is considered as an effective strategy in climate change mitigation, but seagrasses have not been included in in climate change policy. To include them in the climate change policy, we have to understand more about carbon dynamic in these ecosystems. But next, please. But the lack of information about the factors responsible for this variability could limit us to formulate strategy in the climate change mitigation based on seagrass carbon sink capacity, such as we all need to estimate like how much carbon is stored, then we can also estimate how much carbon is being released, and then how much carbon is accumulated in the sediment, and then we could also estimate how much carbon sink capacity, carbon sink potential capacity. Wait, one more. Could you, yeah. And one more, we also need to estimate the carbon sources, from where the organic carbon is derived from. Because carbon in the sediment could be derived from the primary productivity, or could also derive from surrounding areas, or we also call it allochthonous organic matter. So in this, so in this study, we tried to identify the sources of organic matter, the sediment organic matter, and analyze their contribution to carbon stock in seagrass ecosystem. For this study, we did it in Spermonde Archipelago, which is the same place where Bu Rohani did research. And next. Yeah, like I told you, this is the similar place where Bu Rohani did her research, and we sampled biomass. We also collect samples, sediment samples, and we took samples in 4 different areas which have different characteristics. In the inner, in the middle, and in the outer, and one in the island which is not surrounded by other islands, which is directly exposed to waves. So what we did, we analyzed we analyzed the sources by using carbon isotopes. I'm not going to explain this in more detail, but in general, organic matter have distinct carbon isotope composition, which their individual contribution to sediment accumulation can be resolved through their isotopic signatures. Next. So in this study, we use the stable isotope composition, stable carbon isotope composition, delta 13C, and we also use other proxy, which is CN ratio, because if we only use one proxy, it will be overlapping. So we need 2 proxies. So here, this has been published by other author, and they plot the organic matter in different in this graph, and we could see that every organic matter has different signature. So that's what we did. Next. Just next. Please, next. Yeah, this is from our study. We plot our samples in this graph, and I don't know if you could understand this, but I will explain briefly that the dot with straight line represent the organic matter, the sources, and our samples are in each dot, yeah, over there. So I will explain briefly the result here. If you see the dots over there, I don't know, can you? Yeah. Anyway, but those 3 dots over there represent area of Kapoposang, Sarapokeke, and Sarapokeke Baranglompo, means those areas which is surrounded by many islands have the sediment organic carbon derived mostly from seagrass. However, in Bauluang Island, which is located downward, which is directly exposed to waves, the organic matter mostly derived from coastal POM, or in here probably ceston or phytoplankton. So this probably because the Bauluang Island is directly exposed to ocean, without barrier for surrounded islands. Next. So we also analyzed the contribution, how much percentage the contribution of each the organic matter to sediment organic matter. If you look at the of those graphs, the Barang Lompo, Sapokeke, and Kaposang, they have high contribution of seagrasses to the sediment organic matter, while in Baoluang, the predominant contributions comes from coastal organic matter, coastal particulate organic matter, which could be ceston or phytoplankton, which almost 70% comes from coastal POM. And yeah, next.
Ibu Mariska,
yes,
time is almost up.
this will be the last. So if you see the biomass, it's interesting because despite having the high seagrass biomass, Baoluang Island has the lowest sediment carbon stock compared to other islands. And the accumulation of non-seagrass derived organic matter probably resulted in a lower sediment carbon stock in Baoluang Island. And the non-seagrass derived organic matter might not be sequestered because the compound is more labile and easily decomposed compared to seagrasses. And therefore, the autochthonous organic matter or the primary production might have diluted with carbonate, which resulted in a lower sediment carbon stock in Baoluang. Next. This is the preliminary conclusion that the variability of sediment organic carbon in seagrass ecosystem in the Spermont Island was determined mainly by geomorphology and hydrodynamics, in which seagrass meadow with direct exposure to the ocean receive high allochthonous organic matter than those islands which is surrounded by many islands. And dilution of autochthonous organic matter or dilution or primary production with the allochthonous inorganic carbon such as carbonate, and also the low retention of non-seagrass derived organic matter likely resulted in a lower sediment carbon stock in Baoluang Island. And this within system variability of organic carbon deposition in seagrass needs to be taken into account when we constructing seagrass carbon budget or when we develop climate change mitigation strategies. Thank you.
Thank you very much. Big applause for Ibu Mariska. And the last speaker for this session, Ibu Atika Rahma.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Let me introduce myself. My name is Atika Rahma. I'm actually an undergraduate student of Department of Biology, University of Indonesia. So here I'm gonna present my research. Actually, this is not about seagrass, but it's about seaweed. But maybe it might be something new for blue carbon issues in Indonesia. So because I prepare the material in Bahasa, so I will speak in Bahasa. Next, please. Berikut outline-nya. Next. Seperti yang kita tahu, usaha mitigasi perubahan iklim saat ini juga sedang memfokuskan pada sektor laut, di mana laut dapat menyaingi hutan daratan dalam menyerap karbon dioksida dari atmosfer. Karbon yang diserap oleh vegetasi laut dan pesisir disebut juga blue carbon.
It was conducted at Banten Bay and Derawan Island through vegetation and mangrove and Ambon, but There are only limited researches on blue carbon and macroalga. Macroalga is a plant with chlorophyll living on the sea, and the growth is affected by the light, temperature, salinity, pH, oxygen, and also hydrodynamic factor. And then there are the groups of this macroalga is Hydrophyta, Chlorophyta, and Phaeophyta. Macroalga has a lot of potentials in carbon sequestration. It tends to not survive in high tides. But one good thing about it is that macroalga is distributed in 8.6% of total sea biotas in 1.2 hectares, and then they are strong in terms of sequestration of carbon. So although they have to be deplanted because of the tide, they can still sequester carbons. And in Muara Binangan, the macroalga production could reach 5 tons per year, and there are types of macroalga that can sequester carbon. The first one is Gracilia verrucosa and Halibada opentia. Gracilia verrucosa is mostly found at Binangan and saves 60% of carbon in the form of carbohydrates, and the carbon content is 19.56%. And they can absorb carbon in the forms of other substances. And then the other one is Halibada opentia. It consists of 0.68%. But Halibada opentia hasn't been utilized for economic purposes, unlike Gracilia verrucosa. While for red and green algae, they can do classifications to store carbon. These are the characteristics of Gracilia verrucosa. They have stems, and they live in shallow water, while the green one lives in groups in a hard substrate. Therefore, for the calculation of carbon sequestration, we can check the level of macroalgae growth, and also by measuring the carbon fixation. The primary productivity can also be used as a measurement, and also productivity of net and gross productivity of net primary and gross one. So the objective of this research is to compare and to identify how much is the carbon sequestration in Muara Binangan. So this research was done in Muara Binangan in March 2018. We chose 2 stations where the 2 types live mostly. These are the tools and equipment, and then we measure the environmental parameter, and then we did light and dark bottles. We prepared 8 bottles per species, 4 are dark, 4 are light, and each 4 consists of 1 control bottle and 3 containing macroalga, and then all the bottles are filled in with water and without oxygen, and then the bottles are incubated for 3 hours, and at the end we measure again the oxygen content. We also consider the plot methods of macroalgae density by measuring the coverage of macroalgae. And then the next one, for the dry weight, we calculate by doing the wet measurement, and then we use the oven, and tenure at the rate of 600 degrees Celsius for 3.5 hours. And next is the calculation formula to identify the primary productivity, and the gross primary productivity and the net primary productivity is calculated by using the gram carbon per meter cubic per day unit. And then we also calculate the microalgae density, so mass per plot divided by the total area of the plot. Then we come up with the carbon sequestration per meter square per day and carbon storage by calculating the net primary productivity. These are the results. These are the results of the carbon sequestration. The average sequestration of Varicosa is higher than Opuntia. Opuntia is higher than Varicosa, and this is because of the things that I mentioned before. I explained before. And as we know, the primary productivity is affected by the sun, the temperature, and the nutrients. And we use 1 to 2 segments per day. And Halimeda opuntia grows in groups, so that the density level is higher compared to Varicosa, and they form thick meadow. And for the carbon storage, the average of carbon storage for Opuntia is slightly higher than Varicosa. And this is because the net primary productivity is higher than the Opuntia, so that the carbon storage is lower than the carbon sequestration. And is also affected by the biomass density of Opuntia, which is higher. And the productivity in the nature is closely related to microalgae morphology, because microalgae has higher productivity, says Varicosa, which is higher, 1.6 times higher than the other one. And for stronger species like Opuntia, they have fewer photosynthetic cells, so that it slows down the production rate. Meanwhile, for Hybridia opuntia, the surface is wider and thinner, and it affected the efficient process and the carbon sequestration. And this is the content of carbons and carbonate. So we found that Opuntia is higher than Varicosa in terms of carbon storage, and the carbon dioxide will infuse with water to the surface, opponent surface of microalgae, and then they will mix with the chlorophylls, and then the content will be useful for photosynthesis process, and then they will also produce carbonate and mineralization in new segments.
Kadar air dan kadar abu next. Diketahui bahwa
And we all know that the water content is higher in Varicosa compared to Opuntia. Therefore, Opuntia's carbon is higher than Varicosa, and then the ash content of the Opuntia is higher than Varicosa, and it is expected that Opuntia will use it for better classification. So the conclusion is that microalgae is one of the sea vegetations that needs to be considered, and then carbon for Opuntia has high potentials to absorb carbons, and then the organic and inorganic carbons is higher. And for the suggestions, I would suggest more researches on other types of algae, and also with additional variations of time and methods, and we also need conservations for other microalgae that has potentials to absorb carbons and the capacity like Apuntia. That would be all from me, and thank you.
Give us, give a big applause to Bu Atika. You can sit in front, and I ask our speaker, please come. So we actually not outside one by the speakers. You can ask question, but please do not give lecture. Question, okay? Question that can be directly answered. And I hope the speaker can give a short answer, direct answer, not giving also any lecture. Please.
In interpreting your data, Mr. Aan Wahyudi, I think, comma to express, measure, weight, and others. To me, when you use the English language, comma means point. But if you use Indonesian language, points means fraction of a number behind the point. That, I'm sorry, I have difficulty to interpret that, because you mix the notation of comma and points. To the first speaker, that was Ibu Rohani, do you really think the difference of latitude between Makassar and the northernmost point is significant to the difference in your finding? That is my questions. And to the last speaker, I really also have difficulty to interpret. I'm a layman in this case. I'm not a scientist in your field, but it would be better if you will be more systematic in explaining. For example, there are collection of 2 islands on the Strait of Makassar, which where you mentioned about the Kalupuang? Kalupuang. Second from the last, yeah, second from the last. Kalupuang. Yeah, what? Kalupuang. There are two groups, but which one you mention it? You only mentioned one. And for me, man in the street is very difficult to interpret that. Thank you very much.
Thank you very much, sir. So please, speaker, who have the question, please answer. Okay, so I think for the second speaker, I think this is a mistake in the copy and paste for the textbook for Kalapusang. Okay, so for the Pak Andri, you want to answer? Maybe clarification, whether it is really comma for 1,000 or decimal.
Maybe we skip the number, but if you the number, we can give you the data. After we correct the data, we can give you the data. Yeah.
Thank you. Ibu Rohani, please.
Yeah, thank you. So I'm very sure that they are significant because I already analysis. So the standard error is very small. That's why they are significant. So because the data have been analyzed and then they are significant, that's why I come to the conclusion that wave exposure especially could affect the carbon capacity of the seagrass.
Thank you. So we still have maybe one more question from the floor. Is there any question from the floor? One more question? Or we have enough for today? I think we came to the conclusion that blue carbon is important and seagrass is one of the things that we need to consider. that connect to the seagrass and the surrounding area can and will become the main agenda in national and become a way to support the global commitment. Thank you very much for attending today. Let us give a big applause once again to the distinguished speaker today. Thank you for the great presentation. I hope we have more time, but I'm sorry I need to make the session very short and precise in time. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh. And photo session, okay, with all speaker.